Hi everyone and welcome to my channel. My name is Lewis and I'm a qualified accountant. For this video, I want to talk about the most influential equation in finance in my opinion, and that is the time value of money. This equation is so influential, it drives the underlying mechanics of every single debt product in the market. But really it can be applied to anything that represents monetary value. For example, equity instruments, mutual funds, properties, insurance premiums, the list goes on and on. But I'm gonna do it in a way that's not been done before. You see, finance textbooks and in general, the way this topic is explained is that they go straight into the equations without giving much context, much intuition behind the equations. Where do they come from? Why are the equations what they are? More accurately, we are going to derive the time value of money from first principles. So I'm going to start off with a simple intuitive example. Over here is a £50 cash note from the UK. Whether I spend this money today, a month from now, or in a year's time, the amount isn't going to change. But clearly, the purchasing power of this cash note will fall over time because of inflation and other macroeconomic factors. So we can already tell that the value of this cash note not only depends on its notional amount, which is the amount that you see on this note, but also on time. There is a time component, and actually there's a third variable, and that is the inflation rate, or whatever discount rate that you want to use. Okay, so to help us understand how money depreciates over time, it would be helpful to use some sort of visual. So over here I've got a value on the y-axis and time on the x-axis, and we want to see how the value of our cash note drops over time. Let's say that at t equals to 0, which is today, the value of our cash note is equal to £50, which I've labeled as point A, and after t years in the future, that value drops down to point B is equal to x pounds at t years in the future. The value of x or t isn't relevant at this point. For example, x could be anything below £50, such as £45 or £40, and t could be 1 or 2 years from now. The point of this exercise is, can we model our cash note using an elementary equation? For example, could we use a straight line equation with a negative gradient? Does it fall linearly over time? Or is it some sort of curve, like so? Well, it turns out that the best model for a cash note is a curve, specifically an exponential curve. The notion that £1 today is worth more than £1 in the future is the very definition of the time value of money. Now, in order to understand the exact relationship, we need to take a step back and build our intuition about wealth first. I'm sure you've heard the phrase before, the rich get richer and the poor get poorer. But why is that? Well, the person who has greater wealth has more resources, i.e. has more spending power. They can use that capital to generate more wealth over time through various investments. And those investments do not grow linearly over time. In fact, they tend to grow exponentially. We can express this algebraically as the absolute growth in wealth, delta W, over that time interval, delta T, is proportional to wealth itself, W. Again, what this relationship is basically saying is that the more assets you hold, the faster your wealth can grow, which is a very intuitive and simple assumption. Now we are missing one more term, and that is the growth rate R. I've assumed R to be positive and a constant, but it doesn't have to be. If it is positive, it just means that the average growth is positive and wealth grows over time. And if it's negative, then that just means that wealth falls over time. Interestingly, if R is not a constant, i.e. if it continuously changes over time, and anytime you think of continuous change, you think of calculus. And in fact, the actuaries call this the force of interest, and they've labeled it as delta, which is equal to the integral of some starting point t1 to an end point t2 of R, which is the interest rate that continuously changes over time, so it is a function of time, times the variable of integration, small dt. However, for the purposes of this demonstration, we can safely assume that R is constant, and to be honest with you, in most practical situations, it is almost always assumed to be a constant, and I will touch on this more later in the video. Now let's try to solve this. By that I mean, is there an elementary function out there that satisfies this relationship? Remember, W, wealth, is not a static figure. It varies over time. Now let me just re-emphasize that because R is positive, the average rate of growth must also be positive. So that's delta W over delta T, which in turn means that W is increasingly positive. It can only go up. Now, if you've ever done high school mathematics, you know the solution to this equation. You probably solved it using calculus. However, let us try to do it using algebra instead. As a starting condition, let's say that at t is equal to 0, the value of our wealth, W, is equal to W naught, which is an arbitrary constant. It can be, for example, 1,000 pounds, 10,000 pounds, or 1 million. Doesn't matter. Now, after some time delta t, we have T1 is equal to T naught plus delta t. And the value of W at that point is W1 is equal to W naught plus delta W naught. However, we can define delta W naught in terms of this relationship up here, which is our initial intuition, which is that the more assets you hold, the faster your wealth can grow. So I can plug that into delta W naught. So that means W1 is equal to W naught plus delta T times R W naught. And if we just factorize W naught out, we have W naught 1 plus R delta T as the value of W1. And we keep iterating until we see a pattern. So let's try the next data point. T2 is equal to T1 plus delta T. The value of W at that point is W2 is equal to W1 plus the absolute growth at W1. And we know that the absolute growth is given by a relationship above, so which is R delta T W1. And if we express W1 as W naught, shown above, that means it is W1 1 plus R delta T is equal to W naught 1 plus R delta T 1 plus R delta T, which is simply W naught 1 plus R delta T the whole squared. So hopefully you can start to see a pattern here. We can write a general expression for Tn now and Wn. So let's just do that now. Tn is equal to Tn minus 1 plus delta T. And the value of W at that point is Wn is equal to W naught 1 plus R delta T to the power of n. So we've now proved that the solution to the expression above is an exponential equation. And it's an exponential equation because W naught, R, and delta T are constants. The only thing that is variable is n. However, this is not the standardized time value of money equation. We can think of R as the rate of return with units of percentage per annum, for example, 10% return per year, and n being the total number of compounding periods. So we can define t years as n times delta t, and n is equal to m compounding periods per year times t years. Now I'm just going to remove n on the left hand side. So that's simply mt times delta t. The t's cancel. So we have delta t is simply 1 over m. And we can plug all of this to our equation above. W is equal to W naught 1 plus R over m to the power of mt. And this is the standard time value of money equation. Just to be clear, m is the number of compounding periods per year, t is in years, and r is in percentage per year, which I'll write here on the right hand side. Now you might be wondering, where does the exponential equation come in? You may have seen the letter E before. Well, as m approaches infinity, the accumulation factor, which is this base over here, approaches a limit. In fact, one of the ways of defining Euler's constant is by setting r is equal to t is equal to w naught is equal to unity. And then see how the equation varies as m gets larger and larger. We can set up a table with increasing values of m. So let's just say that m, being the number of compounding periods per year, is once a year, twice a year, 4 times a year, 12 times, 52, 365 days a year, or 8,760 hours per year. And we can go even further, 525,600 minutes. And just for demonstration, we can express it in terms of seconds, 31,536,000 seconds per year. And we plug that into our equation W and see how W changes. Well, if we plug m is equal to 1, that is equal to 2. If it's 2, then it's 2.25. And I'm just going to write the rest of this down. We can clearly see that as m gets larger and larger, W approaches a limit. And that limit is 2.7182 in 4 decimal places. And it goes on and on forever. It's an irrational number. This number is so special in mathematics and really in nature that we've assigned a letter to it, and that letter is E, which also stands for Euler's constant. So we can rewrite our time value of money equation as, in the limit that m approaches infinity, W is equal to W naught 1 plus R over m to the power of mt approaches W naught e to the power of RT. Now, before we move on, let us practice our knowledge using some examples. So Ben invests £10,000 in shares that pays at a dividend rate of 7% per annum. What is the total return after 5 years if dividends are paid annually, semi-annually, monthly, and every instant? So for the first part, hopefully you can see that m is equal to 1 because dividend is paid once a year. The value of W becomes £10,000, 1 plus 7% over 1 to the power of 1 times 5, because we want to calculate the total return after 5 years, so t is equal to 5, and that is equal to 14,025 pounds, and 52 pence. For the next one, dividend is paid twice a year, so the number of compounding periods per year is equal to 2. So let's figure out what that new value for W is. That is 14,105.99, which is higher than the first one. For the next part, dividend is paid every month, so it compounds 12 times per year. M is equal to 12. And this value will be even higher than the one before. 10,000, 1 plus 7% over 12, power of 12 times 5. That's 14,176 and 25 pence. And for the last one, dividends are paid every instant, which of course is practically impossible, but it will help me explain the next section. So let's just compute it now. M is equal to infinity, and that means W is equal to 10,000 pounds, E to the power of 7% times 5. Remember, E is equal to 2.7182 in 4 decimal places, and that is equal to 14,190 and 68 pence. Now notice for the same 7% return, as we increase the number of compounding periods, we're able to generate more wealth. If we go back to our cash example at the beginning, we said that at t is equal to 0, the value of our cash note is equal to 50 pounds. So that means W naught is equal to 50 pounds, which is the value today. And that value, we said that it may drop down to X pounds at t years in the future. Let's start putting in some assumptions. Because cash is a depreciating asset, it's not generating a return, R is negative. So let's just say R is equal to minus 5% to represent the fall in value of the pound. Let's say it's been put in a bank, it's not doing anything. And we want to know the value after 1 year. So that means t is equal to 1. And for these types of questions, we can safely assume that the number of compounding periods is just equal to 1. And with that, we can find the value of our cash note after 1 year. If we just write down the equation, W is equal to 50 pounds, 1 minus 5% to the power of 1, which is equal to 47 pounds 50. Of course, these are made up figures, but this was just to show you that wealth can fall just as much as it can grow. So when do we actually use Euler's constant in practice? You see, the reality is there's not a single financial product in the market that compounds an infinite amount of times per year. It is simply not practical due to the discrete nature of transactions. We can record a sale, a transaction between two parties, every hour, every minute, and perhaps even every second, but not every instant. Remember, in order to have daily compounding, money must be credited into the account every single day, and that should compound every day. That's the most frequent compounding I've seen in the market. Trading 212 used to offer that with their cash ISA, but that rule got changed recently in January. And to be honest with you, that specific product under those conditions didn't last very long in the market. May have been for less than 12 months. So it really isn't that common. So that means that in order to have infinite compounding, money must be credited into the account an infinite amount of times per year, which sounds ridiculous, and frankly, there's not a single IT system in the world that is capable of doing that. However, I do think that in certain restrictive situations, we can mimic infinite compounding. For example, if the account is locked away for a certain period of time, which means that the investor cannot add or withdraw funds from the account, and the proceeds are automatically reinvested in the background. But I've yet to see that being done in practice. Really, the value of using the exponential function e to the x is when we deal with continuous change, such as the force of interest delta that I touched on earlier, in which the interest rate continuously changes over time. It significantly simplifies the mathematics and it makes it more elegant, but it is an extremely theoretical scenario, which is why it's more commonly used in academia, not in practice. It is a mathematical ideal. In the real world, transactions are discrete by nature, i.e. they happen at finite points in time, which is why e to the x is rarely, if ever, used. Before we head off, I want to talk about simple interest. So this is a page from my physics formula book from when I studied at Cardiff University. This will be a great source of reference for the next couple of videos when I talk about mortgages and savings accounts and so on. But I want to briefly talk about simple interest. When do we use it? Well, it's commonly used for products with maturities of 12 months or less. Think of treasury bills, commercial paper, and many other short-term debt securities. If we were to define the exponential function in terms of the Maclaurin series, which can define any function as a series of polynomials, then our exponential function would look like here on the right. Now, I've already written it down because to derive this, it's beyond the scope of this video, and to be honest, I don't think it's going to aid much of your understanding. But I just want to re-emphasize here that all we're doing is that we are expressing the exponential function as a series of polynomials. That is what the Maclaurin series does, the Taylor series, the binomial series. It's just a way of expressing an elementary function in terms of polynomials. Now, interestingly, as r and t approaches 0, which means they become very, very small. If you remember, r is the interest rate per annum and t is in years. As they become very small, the series approaches a limit, right? And that limit, let me just write that down, is equal to w naught e to the rt. It approaches w naught 1 plus rt, which is simple interest. If you look at the numerators over here, as R and T is very small, which is usually the case with short-term debt securities, the interest rate is very small, and the time is also, in days, weeks, months, and up to a year basically. All these other terms, all the higher order polynomials become very insignificant, and so it approaches this formula. And if you know anything about polynomials, is that this RT is simple interest because there's no compounding term. And I just want to remind the audience the difference between polynomials and exponential functions. A polynomial has this form, x to the n, where x is the variable and n is the constant, which is different to the exponential function, which looks very similar, which has a base a, which is a constant, and the variable is the exponent, x. And of course, the exponential function, which is when the base is equal to Euler's constant, e, and obviously, again, the index is x, and that's the variable part. So this is essentially how you can derive simple interest, which is when the interest rate and time is very, very small.